My talk will be on energy storage and the role of interfaces from the standpoint of solid-state electrochemistry. And what you see here in the next slide is the skyline of Singapore. And the bottom part is liquid, even though it looks like a mirror. The middle part is a solid-state part, and the upper part is a gaseous part. And as you see, structuring, at least durable structuring, is only feasible in that middle part. And the reason is that the solid state provides rigid bonds between the atoms, at least at room temperature. And these are reflected by the diffusion coefficients that are pretty low in the solid state. So this is a list of diffusion coefficients. And the second column here gives the time that a signal needs to be diffused out over a distance of 1 millimeter. So when you have 10 to the minus 2 or 3 centimeters squared per second, these are rather large values for solid state, very unusual. They are rather typical for the liquid state. So in the liquid state, it takes only a second or so for the diffusion. So that means a structure from a diffusional standpoint cannot be stable over a long time. So you cannot structure water, for example. So when you go to more realistic values that are here shown when you go upwards towards maybe 10 to the minus 10, still a high value at room temperature, then it takes PhD work typically, so several years, until the signal has diffused out. And 10 to the minus 20, by far not the lowest values that you can find at room temperature, then you have already exceeded the Earth's age. And that means then you are pretty safe in terms of structuring solids as far as the diffusion is concerned. This is a solid-state ion conductor, and this is zirconium oxide. It is appropriately doped such that the oxygen sublattice becomes mobile. You have a lot of vacancies in there. And at high temperatures, this crystal can be used as electrolyte for fuel cells, with the help of which you can convert hydrogen and oxygen to water electrochemically. But still, in spite of this, the crystal behaves like a solid, and it is a solid because the zirconium ions are very sluggish. You could use a single crystal as an electrolyte, but of course it's a little costly. It's rather used as a gemstone. What is used in practical devices are these ceramic tubes, and ceramics are sintered single crystalline parts. And the grain boundaries, the boundaries between these crystals, they should be not very resistive. But there is also the other side of the solid state where the interfaces play an enormous role. And this is an example that we will address later, a nanocomposite of ruthenium and lithium oxides. We see here the nanoscale. It's full of interfaces, and then here the interfaces dominate completely the transport behavior, or the storage behavior even. So it's all about charge carriers when it comes to electrochemistry, no matter if liquid or solid, or even in the gaseous phase when you talk about plasma. And let me spend a little time on this. So this is a section of the water structure. You see not only H2O molecules, so you also have a dissociation, as you well know. So you have HCO plus ions and you have OH minus ions. And they are highly important for the properties, but they are defects. They are due to entropy. To form them, it costs you energy. So if you abstract from it the underlying perfectly thought water structure, then you have isolated, so ignore here the nomenclature, it's not important, the excess proton and the lacking proton, the proton vacancy as it were. So these are point defects in the water structure in a snapshot kind of way. And this kind of defect concept is something that is most important for the solid state. So this is a section out of a rock salt structured silver chloride, and the silver ions also undergo a disorder. So you have silver ions here where they do not belong, like in the previous example, you have vacancies left. And this is again due to entropy. And when you abstract from the 0 Kelvin perfectly thought structure, then you have isolated the silver ion here, an interstitial site, and the vacancies. And again, the same you have in terms of electronic disorder. Let's consider an oxide, maybe tin oxide, zinc oxide. Let's take zinc oxide, Zn2 plus O2 minus. It's not always like this. You have a certain disorder, you have some zinc plus and you have some O minus. So this disorder or transition of the electron from here to there comes or means transition from the valence to the conduction band. So if you do, and again, this is due to entropy only. When you subtract the underlying perfectly thought situation, then you have isolated the excess electron in the hole. This is always the same game, lacking particles and missing particles. As defects, they determine the transport behavior. So much is about language. And so I had the ambition here to use the same language for all the cases. Let's take silicon as an example of an electron transfer now. This is the transition from the valence to the conduction band. You bridge the electronic gap. You know, there are some examples where this gap is 0, then you speak of a metal. Then all the electrons involved here are disordered or free. On the left-hand side, you see the water situation. You bring the proton from a water molecule, bring it to another one, form HCO plus, leave behind the OH minus. So you bridge the ionic gap in the phase of water. And if you have a material or a solvent where this is 0, this gap, then you speak of a strong electrolyte. And this is a solid situation where silver ion is transferred from the regular level to an interstitial level. And this also may, in some cases, be 0, this kind of gap. Then we speak of a super ion conductor. And we will later meet one of those, this rubidium silver iodide, where this gap is virtually 0. So every silver ion is then disordered. The semiconductor people, they insert electrochemical potential of the electron. It's not so important what it is at the moment if you're not interested in it, but it's a decisive quantity. Also, the Fermi level is another term for it, such that the distances to these levels are measures of electron and hole concentration. So if you take the same analogous quantity for the proton, then you can put it here in the middle again or somewhere in between, and then you have pH and pOH. And when you do it for the solid crystal, then you do the same here with your disorder of silver ions, and you have then to care about the electrochemical potential of the silver plus, so the analogous quantity. Dopants also have a similar role. The phosphorus in a silicon excites an electron to the upper level, and this level here is characteristic of it. On the left-hand side, you have water. This is an acid, acetic acid. This is a proton donor, and you can plug in these characteristic levels within this gap. That would be the semiconductor language of what the chemists know an acid-base scale. The same here with the silver ion. I think needless to say that everything is very much analogous, and the details are not so important, but keep in mind the description is very much the same. And everything can be described in terms of classic mass action law as a chemist do in water. One thing is important, namely that you have a coupling between ionic and electronic disorder. So imagine you have silver chloride, you have this ionic disorder, but you also have a band gap in silver chloride. Now we put that electronic picture upside down, and then this distance, which is in fact then the sum of these two levels, is the chemical potential of the neutral silver. That means it measures how much the free energy increases when you add silver, but at the same chlorine content. So you change stoichiometry. Stoichiometry is an important parameter in the game in determining the carrier concentration or the partial pressure of the component is a means of doing this. Like we will see oxygen partial pressure in oxides. Temperature is, of course, another one, and doping content is a third one. So let's go back some 200 years. This is an old controversy in chemistry between John Dalton and Claude Louis Berthollet. And this was before the atomic theory was well established. So Dalton had the idea or the impression, which of course is a correct one, that you have combined atoms in very clearly defined proportions. Berthollet had the opinion, oh, you can change these things in a continuum way. Berthollet was not completely incorrect when it comes to solids, because if he had been completely incorrect, there would not be an insertion electrode in lithium-based batteries. So this is a typical phase in the phase diagram. Let's take an oxide, maybe zinc oxide in between zinc and oxygen. And this is not a line phase. You have a certain range of stoichiometry. You have deviations from that one-to-one composition. Maybe very small, maybe not even variable. But what happens when you go through it, and you can go through it by changing the oxygen partial pressure over it, that is shown in this complex diagram. It is of dramatic influence on ionic and electronic carrier concentration. So when you go through this tiny thing, the electron concentration goes down a lot, excess electron, N-type. Hole concentration, P-type, goes up a lot. Vacancy concentration, so the ionic important species, goes down a lot, and the oxygen interstitial goes up a lot. So you change essentially this material from an N, maybe via ion conductor to a P-type conductor, only by going through this ppm maybe of phase width. And this is most important. So how can one measure these kind of things? And how can one vary these kind of things in an electrochemical way? And here I took silver, could be selenide or sulfide or telluride, and we explore that phase width electrochemically. This can be done by having an electrode on one side, platinum, and another set of electrodes on the right-hand side, silver iodide and silver. So when you pass a current, the electrons come from here. From this side, the electrons change into a silver ion conductivity, because this is a pure silver ion conductor. And then silver ions come from the right side. So when silver ions come from the right side and electrons from the other side, you form silver and you dissolve it in the silver chalcogenide. This is called a coulometric titration. This is highly precisely measurable. And when you look at the cell voltage as a function of that small deviation from the one-to-one stoichiometry, then you get these characteristic S-shaped curves. They correspond to very tiny phase width. So we speak here of a chemical capacitance, because it shows how much an uptake of a mass or an atom or whatever can be when you change your partial pressure, your chemical potential. This is a good term, because when you take chemical resistance times chemical capacitance, this is obviously something like a chemical relaxation time. And the chemical relaxation time defines what is called a chemical diffusion coefficient. That is a measure how rapidly silver distributes in that phase here. Now, what is it all good for in terms of energy research? I'll tell you in a minute. Let's go to batteries now. Let's consider an electrode that is a material that has lithium ion and electron conductivity, maybe lithium titanate or lithium iron phosphate or whatever, lithium cobalt. This is a lithium electrolyte, typically liquid one. This is lithium on the other side of your cell, and you have a kind of a current collector that may be copper. Now, look at this. It's exactly the same setup as we had in the silver case. On this side, the electron comes, and from this side, the lithium ions comes. They meet here, form lithium. The lithium is distributed and changes the composition in the mixed conductor. So obviously, a battery cell is a coulometric titration cell. What does it mean is that in order to understand on a higher level electrode materials, you have to look at these kind of strange diagrams. So you have to look on what is called defect chemistry. And then you understand what you do when you add lithium or remove lithium from the electrode material. And look at this. You can derive from that directly such a curve. And this is the S-shaped curve that we have seen in the previous example. It's obviously a coulometric titration curve. This is cell potential as a function of lithium stored. So the charge-discharge curve in a battery. So when you have the opinion, this is just equilibrium and has nothing to do with kinetics, it's not so, because usually the kinetics are determined by the solid-state diffusion that inside is pretty sluggish. And the chemical diffusion has to do with the conductivities of ions and electrons. And they also derive from this figure. So this figure is crucial in electrode research, but almost none in the battery field is looking at these. So how can you store lithium? You can store lithium in that intercalation way just described. So you dissolve it in maybe an oxide. Maybe ruthenium oxide is our master material to consider. You may add so much lithium that your material even changes to another phase, which is lithium richer. And upon adding more lithium, you can even decompose it into a mess of phases here, finally lithium oxide in the metal or even the alloy. And then you have the possibility, as we will see, to store lithium also at interfaces. As I said, our master material here is ruthenium oxide. And when we start out with ruthenium oxide, we add lithium and look at the voltage as a function of lithium content. So this is a charge-discharge curve. This ruthenium oxide has only a very little solubility for lithium, but it changes via more lithium consumed to lithium ruthenate. This is a phase change mode that we also had considered. And within the lithium ruthenate, you can add more lithium than, for example, ruthenium oxide. So it's already a decent storage. And you'll see this S-shaped curve that we have seen. Very huge storage behavior is possible via the decomposition of that material to lithium oxide and ruthenium. Very large. The fact that this is not so far part of modern batteries is due to the fact that these things are hard to reverse because of the mess of phases. You want to go back to lithium ruthenate. And then there is a very interesting part, which looks a little similar than this one. This is an excess storage that you would not even expect classically. And this can be attributed, as we will see, to interfacial storage, what we call chop sharing. And then we come to this kind of picture you already have seen. Imagine you have a nanocomposite of ruthenium lithium oxide, and then this stores obviously a lot. Now we have to go back to our little bit academic profiles, because the semiconductor people deal with interfaces by bending the energy levels. Now, when we do the same for the ions, and we are saying very much is analogous, we also have to do it for the ions, and they have to be bent in the same way because there is an electric field that makes a bend bending in all the cases, and the electric field is the same. The question is rather what determines the electric field, and interestingly, it is very often the ions that are dominant, and then the electrons just follow what the ions dictate them to do. That's very different from what semiconductor people would expect. So let's go a step back here and consider a bulk of a charge carrier containing system. That may in the simplest case be a liquid. Then you have positive and negative charge carriers, or in a solid, you have positive and negative defects. They are equal in concentration. So obviously, the one that is hardest to form will determine the equilibrium concentration. So it may be much, much lower. Maybe you would like to form more negative carriers, but you can't because you need the hardly formed positive carriers in the same way, in the same concentration. So this is obviously different when you go to an interface. And this is a kind of a metaphoric way. We plug in a foil into the solution. And this foil is then, for example, positively charged. You have a charge situation always in a charged carrier containing system. And then you only deal with the negatively charged carriers on one side. You can obviously produce a lot of negatively charged carriers by having this charge separation at the interface. And if you have many interfaces, the effect is large. And the effect is interesting when you go to a mesoscopic situation where these kind of charge, space charge zones overlap, and nowhere in the bulk you have a real bulk behavior. Nowhere in the middle you have a real bulk behavior. So this is a field that is mostly attributed to us, and it's called nanoionics. And there is a whole zoo of phenomena. So this figure is just to impress you. It is not even complete. You find these redistribution phenomena of ionic charge carriers, so point effects, almost anywhere. In terms of solid electrolytes, solid electrodes, as we will see, sensors, catalysts, superconductors, you almost just name it. So let me just mention one. That is a very nice master experiment that we did in Stuttgart. These are hetero layers of barium fluoride and calcium fluoride. Both are fluoride ion conductors. And the interface has a much higher fluoride ion conductivity than the bulk. And we understand the system extremely well. We also understand the transition to a situation where there is no bulk in between. This happens when the spacing of these individual layers is smaller than the length that determines the decay of the space charge zones, as shown here. This was transport, but here I would like to refer to storage. What can we do with these kind of effects in terms of storage? You will see it in a second. Imagine you have that composite that we had, the ruthenium lithium oxide. So none of these two phases can store lithium individually. The ruthenium could store the electron, but it cannot store the lithium plus. It cannot store lithium, which is lithium plus, and the electron. The lithium oxide can store lithium plus. There's plenty of interstitial sites available, but there's no possibility to store the electron to a significant amount. But the composite does a job very easily, and if you have many of these interfaces, this can be substantial. And we know very well how to handle this thermodynamically and kinetically, so I don't want to bore you with this. So when you would like to do some quantitative experiments at room temperature, it's always better to go to silver, because then you can reach complete equilibrium, because silver is much faster. So here we have our already announced fast superion conductor. So I think the G is missing here, the rubidium silver Ag4 iodine 5 together with graphite. So none of these two phases can store silver. Silver is plus is too big to go into graphite. And the electron, you cannot, there's no transition metal ion here which can take up the electron. But when you have the composite, you find very nicely that you get a charge-discharge curve. For this, I would call it artificial electrode, such that you form, you can add silver to it. You have silver interstitial, obviously, on the rubidium silver iodide side, and electron on the graphite side. But you can also remove it. So obviously, you form vacancies on this side and holes on the other side. But this is a wonderful situation when you go to nanoionics, that you can make artificial electrodes that may even evade the conflict between power and energy density. This can be very fast. So imagine you have your silver ion conductor here and your electron conductor there, and you offer the silver here. Silver ion goes here, electron goes there. You have some support from bulk. But when you just look at these layers, then the filling from here and from there is a diffusion. And you can calculate the diffusion coefficient from it. This diffusion coefficient, which admittedly is a heterogeneous one, is the highest ever measured at room temperature. It's more, when you look at this list in the beginning, more on the side of the liquid. And it's even quicker than sodium chloride motion in liquid water. So it can be very quick. The second quickest, we also measured in Stuttgart in a solid state. That was lithium motion in a bilayer of graphene. It's also pretty quick, 7 times 10 to the minus 5. But you see, normal electrode materials, I have not shown them here, maybe lithium cobalt oxide also, they are around here. So there are many, many orders of magnitude less. So I now have mentioned the possibility to vary transport properties by interfaces. I've shown you that the interfaces themselves can give rise to storage, but interfaces are also interesting when they are in a way completely inactive, because you need an interface of your electrode to the current collector where the electrons come from, and you need the interface to the electrolyte where the ions come from. So you cannot dispense with them. And how they are distributed in space is extremely important. So let's go back to our normal intercalation mode where we add the lithium to the bulk. So no interfacial storage here, bulk storage. Electrons come from here and ions come from there, maybe. And the time that it takes is determined by this diffusion coefficient, chemical diffusion coefficient, by the way. And remember our list, when we have a 1 millimeter thick sample, we have 10 to the minus 10 centimeters squared per second, which is a large value still at room temperature, maybe typical for lithium cobalt oxide. It takes a PhD work until the lithium has distributed in a 1 millimeter thick crystal. It's not a good thing. So, but on the other hand, if we go down this size, this goes with a square here, then the same thing, same diffusion coefficient, makes it happen in milliseconds. But on the other hand, if you mill down your 1 millimeter thick sample to 10 nanometer thick particles, you end up with 10 to the 15 particles when you start out with 1. So the problem now is, how can you make sure that any of these tiny particles is connected to the ionic and the electronic current leads? So obviously, for understanding the full situation, we have to look in the modeling. And again, also, as far as the kinetic modeling is concerned, not very much is done in literature, even though the whole world deals with lithium-based batteries. So this is our electrode. The electrons come from the metal side and the ions come from the electrolyte side. So what happens if your mixed conductor is a good electron conductor? The electrons are fast, so obviously everything starts from this boundary into the interior. So it's a diffusion of M, which is M plus and electron, into the interior from the left to the right. It's called a chemical diffusion, ambipolar diffusion. It's indicated here. So on the other hand, if your mixed conductor is a predominantly an ion conductor, then everything meets here and it goes from the right to the left. So now already a riddle for you. What happens if your material is as good an electron as an ion conductor? So this T, which is a ratio of both, or the fraction of both, would be 50%. Would it start from the middle to both sides? No. It will start from both sides with a probability of 50-50 into the interior. So this one-dimensional case is understood. But now we have to deal, because we want to understand the morphology, to higher dimensions. So this is a two-dimensional situation, which already does the job more or less. So here we have the contact to the electrolyte, and the orange one are the contact here to the electron conductor. The same game. If your material is a good electron conductor, obviously everything starts from the ionic contact, so from these long contacts into the interior. It's a very small distance to overcome for this shape. So this is very quick. But on the other hand, if your material is a good ion conductor, then diffusion starts from the sides. And this is very bad because it takes a long time. So obviously, this is then not a good morphology. In fact, you can show that this kind of anisotropy and this kind of oblong shape is best for 6% of ion motion. Now, what is important here is the following. We know the electronic and the ionic conductivity of the electrode, and then we can predict the right shape. And this is not academic, because this might not be a single crystal. This could be also a powder agglomerate, what we typically have in a battery. This is very important. So you have a powder agglomerate here, and here we have electrode particles of which we assume that they are good electron conductors. So if this is so, then you can be pretty relaxed with your electronic contact. So it can be far away from the middle, the next electronic contact. We call it an electronic wiring length, can be far away. But not so for the ion contact. This has to be very, this mesh size, so to speak, has to be very small. So knowing this, simple consequence would be you can spare a lot of graphite that you have to add normally. Or the other case would be, if this is a good ion conductor, then you can be very, very sparse with your ionic contact. This is exactly what you want when you have a solid-state battery. You don't want to have many solid electrode contact. So it's good to look for electrode materials that are pretty good ion conductors. So morphology is extremely important. And everybody knows if you have a certain material, to say this is a good electrode material is not a good term, because it depends very much on how you shape it, how is your distribution in the electron. So I give you here one example that shows it very nicely. This is tin in carbon tubes. Tin is a very good anode. In principle, it can store a lot of lithium, but it cracks because of volume expansion. But not so here. We have tiny tin particles that are mechanically separated, so there will not be any crack. But they are electrochemically not separated. They are connected because the electrons go along with carbon, and the ions come from the electrolyte here and do not have a big distance to travel. The whole carbon tube collects these kind of particles, so you don't need a binder. It's, in a certain sense, a perfect electrode structure. But what this picture should show is that the complexity of electrode in a modern battery can be very high. And it may be as high as the complexity of an integrated circuit or a neural network, but for different reasons. So here you have electronic functions to integrate. Here you have ionic functions to integrate. Here the complexity comes from the fact that you have both. You have ionic and electronic functions to integrate. A final word with regard to that big capacitive regime in the middle that we have not yet addressed, that is this conversion reaction, where you start to form out of lithium ruthenate here, lithium oxide and ruthenium. Then you have obviously a mess of phases. So how can this possibly be brought back when you charge your system again? That's not too bad. When you have your composite ruthenium lithium oxide, you see on lithium extraction can, at least partly, form ruthenium oxide. The key is the small distances, and diffusion is very, very quick. An even better example is molybdenum sulfide. This is a very nice example because it shows how conversion reactions can be made reversible in principle, namely storage in a nanodot. So here we included in carbon fiber about 70% of molybdenum sulfide nanodots, but they are as small as you can do them. There's a single layer in this direction, it's 0.4 nanometer, and the other directions is 4 nanometers. So it's really small. So when you then make this decomposition in the conversion reaction to lithium sulfide molybdenum, then everything is confined on the area of 1 nano, on the scale of 1 nanometer. So it's not hard to believe that this can be reversed. And you see the charge discharge curve here, no, the capacity as a function of cycling is just wonderful. It's like a normal insertion battery, even for a high current. By the way, it also works for sodium. So I still have maybe 5 minutes. Let me just briefly go to another field, because I just want to show that these considerations are not everywhere in solid state, not just batteries, but also photovoltaics, for example, in which we looked recently into. And a very important photoabsorber, which now is probably one of the most important or the most busily investigated solids worldwide, are these hybrid perovskites, where electron-hole excitation happens on illumination. It's perovskite, and in the middle of it here you have typically organic cations such as methylammonium or formaldimine. And unlike the usual perovskites where the anion is an oxide ion, here we are dealing with halogens. Only mention 2 points. One is, again, the charge carriers, electronic and ionic, are to the fore. And before we started, people reported a variety of so-called anomalies. They said, oh, these materials are ferroelectric, very high dielectric constants, which is not true. We measured it. Or there is a lot of hysteresis involved, which is true. But there are no anomalies. It's just exactly what you expect from a mixed conductor, from a solid state ionic point of view. Because you do not only have electrons, you also have ions. Imagine you have such a material and you measure it with a DC current or so, or AC, between 2 electrodes that block off naturally the iodine ions. They block it. So what then happens is you accumulate the iodine ions on one side, you deplete them on the other side, so you go through that phase width that we have discussed. Now, position-wise, from the left to the right electrode, or in terms of impedance spectroscopy, you do not only see a normal response, which gives you the total resistance here, but there is then this phenomenon at low frequencies, which comes from blocking, so that at 0 frequency, you only measure the electrons that can go through the electrodes. And this material has quite a high ion conductivity, so this can be very different from this one here. And it takes a while. And this gives rise to all these strange phenomena. Again, you have to deal with the strange diagrams that take a while to get adjusted to them, but don't worry. I just want to mention they explain the situation in at least in equilibrium. So there is essentially here p-type conductivity, and there is iodine vacancy conductivity. We have shown this by many, many different experiments. So what came to our surprise, and this is important to mention, is that obviously not only the electron conductivity can be enhanced by illumination, but also we found surprisingly that also the ion conductivity can be enhanced. And this is our explanation. The iodine, the hole is an iodine 0 essentially, and the hole may be trapped. And if the hole is trapped in the iodine, then this leads to the fact that it can go to interstitial sites. The iodine 0 is much smaller than the iodine minus and can be further stabilized, and then you form vacancies that you had not before in the dark, and they may be the source of the high ion conductivity. There's one immediate consequence of it. It is what is called photo-unmixing. So you have a bromide iodine mixture, the solid state. What you observe under illumination is that you get a separation into iodine-rich and bromine-rich domains, and this is reversible when you switch off the light. And this directly can be a consequence of what I just discussed, because this kind of effect you only see in the iodine and not in the bromine. So this is my final one. I don't have the time to also show you that the interfacial situation that we have seen before is also very important for these kind of materials. And you have to deal with ionic and electronic redistribution. So for example, at the contact of titania and the methylammonium lead iodide. And the blue parts of the complex diagram here is what you would plot by ignoring the ionic redistribution. So that would just, I would say, in semiconductor physics, you would plot the blue one. But you see, what comes out here is a black one. And this has a variety of consequences, for example, for recombination. So to cut a long story short and to summarize, I hope I've shown to you that solid state ionics and particular nanoionics is important almost everywhere in solid state science where charge carriers are of importance. I gave you examples for material science, in particular here for energy, but equally there are similar things for sensing and information research. It's also important for solid state chemistry. If you think of catalysis, and catalysis on the surface, if we ignore the point defects on the surface, it's just like making catalysis with water by ignoring H+ and OH-. And solid state physics, typically at interfaces, you ignore ion motion, you ignore effects coming from the ions, and we have seen that they may be even dominant in all these cases. So with these examples, I hope I found some interest in the audience for them. I would like to conclude, and thank you very much for your attention.